Here we are with exercise 13. So this and the next exercise are focused on using the singular value decomposition for image denoising. The idea here is imagine we have a corrupted image, we have a noisy image, and we want to see if we can use the singular value decomposition to project out the noise or remove the noise from the data only by removing components. So computationally, this is very similar to the low rank approximation from the previous couple of exercises, but instead of just projecting out the meaningless components associated with the smallest singular values, we are going to remove or project out the components or the image layers, the singular value decomposition layers that are associated with noise. Now, to do this, the Stravinsky image is not terribly noisy on its own, so we're going to add some noise. We are going to corrupt this image using a spatial sine wave. So here is the original picture. You've seen this multiple times before. Here is a noise image. So you can see it's just a spatial sine wave. And then you sum these two together, literally just add this plus this, and you get this, what I call the contaminated picture. So this is the image that contains noise plus the original signal. So the goal of this exercise is to create this image and perform a simple SVD just to analyze this image a little bit. And then in the next exercise, we're going to see if we can isolate these components with the SVD and project that out. And the idea, this is the goal, whether we can start from this image and use the SVD to get back to this image. Maybe it'll work, maybe it won't work, maybe it'll work a little bit, but not really great. We'll have to discover that on our own. Okay, so now here I provide a formula for creating this two-dimensional sine wave, also called a sine grating. And yeah, so sine of 2 pi f, and now this is a sine of two variables, so x and y. And then we have multiple parameters. So there's f, which is the spatial frequency. Here I set that to be 0.02. And then we have theta, which is the rotation angle. That's basically what gives us the orientation here, why it's not just perfectly straight up and down. And here I used pi over 6. Now, you're welcome to use any of these parameters you like. In fact, I encourage you to spend some time playing around with this code and just explore the impact of changing these two parameters on the resulting sine wave image. Okay, and then x and y are grid locations. You can compute those, for example, using numpy.meshgrid. Okay, so then I used integers from minus 100 to plus 100. Needless to say, we are going to sum these two images. So the size of this image, which here I call Z, needs to be the same as the size of the original picture. Okay, so that's the hard part of this exercise, just translating this mathematical formula into code to create that sine wave gradient. After that, it's relatively straightforward. You need to normalize the image. So here's the formula for min-max scaling. Basically, we still want the image to be in the numerical range of 0 to 1. So this will guarantee that this map here has the smallest value of 0 and a maximum value of 1. And after that, I would like you to produce a figure that looks like this. Obviously, you'll recognize this figure. It's exactly the same as before. Yeah, you can copy and paste the code, and I don't think you'll have to change anything, maybe the variable names, but otherwise, this is the same code from several exercises ago. Okay, so then, there's some interesting things to discuss here, which I will talk about when I get to this point in Python. Here we see the code where I create this sine wave image or grading. We can work down from the bottom. So here's sine of 2 pi ft times this matrix x. Actually, I said t. Sorry, that was for time. I'm so used to working with signals. It's 2 pi f and then times all this other stuff, which here I call xp. So xp is this matrix here. So it is the x times the cosine of the phase plus y times the sine of the phase, where these two variables x and y are matrices. They are numpy arrays, which I create using meshgrid. And you just have to make sure you're getting the size correct here. All right, so that is to create the image. And then, yeah, you can see this is really straightforward. The noisy version of the image is literally the sum of these two. And here I'm using min-max scaling. Okay, so here we can see the original image and the noise image and the sum of the two. So then the second part of this exercise was to visualize the SVD. So all of this code you've seen before, and show the reconstruction. Again, this is exactly code that you have seen multiple times before. I've just changed the variable names, but otherwise the code is different. Okay, so let's have a look at this scree plot. Now, remember the non-noisy scree plot of the Stravinsky picture had one big component up here, and then it all dropped very quickly to not zero, but pretty small values that were relatively close to zero. Now, this is pretty interesting. What we see is that there's two additional components, which are, they're not exactly the same singular value. You can see this line here is slightly angled down. There's a little bit of a downward slope here. So these are not exactly the same numerical value, but they do look really, really close. And so what I think is happening here is that the SVD was not able to represent the noise patch, the sine wave grading, as one single component. Instead, it broke it up into two components, but it's the same image feature. So I think what's actually happening here is that this is like an eigenplane or a singular vector plane that is two-dimensional. Okay, and then, that's conjecture is further supported by this image here. So you can see this is layer 1 and layer 2, or the second layer and the third layer, and they look patchy. And what's really interesting is when you sum these two together, I was also adding this, but this pattern is orthogonal to these two. When you sum these two together, you actually do get this grading here. So this is also pretty interesting because when you see this sum of the first couple layers, you don't see the Stravinsky image at all. I guess here, this is supposed to be the head here, so kind of start to see the Stravinsky, but certainly these two layers don't look like the signal part of the image. It just looks like the noise part of the image. And that is the hint that's the segue for the next exercise, where we're going to see if we can just project these noisy components out and what the reconstruction looks like.